thanks, Anthony A. Yeah, I'm going to talk about, actually this is, I've been developing in Python for, God knows, 13 years. So this is going to be a little bit of an arc over the path of development I've had during that whole time, but with a focus on developing for Python and HPC, and really one of my packages is dill, which is probably what I'm best known for now, so I will focus on that as well. Okay, so the part of the, I should mention that I have funding from a couple of these sources, UQ Foundation, which I'm board chair of, but Brookhaven, Caltech, NSF, DOE, DOD, Air Force, and NNSA. And one of the current projects I have right now is this XMetX, Extreme Materials at the Extreme Scale. And it's basically preparation for computing at the exascale. So the idea is I'm part of the DOE Exascale Co-Design Center for Materials in Extreme Environments. It's a DOE ASCR center. It has these partners. And basically, we're looking at what's required for computing at the exascale. The idea is when we scale up beyond petascale, some of the largest machines today, the predicted failure rates say that failure are going to be a part of normal operation, and actually such a normal part of the operation of the system that we can't escape it. There is not going to be recovery. We have to deal with robustness against failure over the ability to do a restart. And we're looking at pieces of the system, pathways, network, chips, etc. So much of it in failure mode, being down, that it's going to have asynchronous and stochastic operation, basically, where we have to have something that is statistics and managing the system at all times, managing the resources and working. So you have to have a working, reliable uncertainty engine as the driver for these large-scale machines. So we're partnered with the Fast Forward projects, which are a big $62 million DOE-funded thing, and we work with Intel, AMD, IBM, NVIDIA especially as the primaries, but there's a couple others. The team, our team, the XMetX team, is made of 7 Bell Prize winners from computer science and material science. I am not a Bell Prize winner. Python folks don't win Bell Prizes. So the Bell Prize winners are primarily National Labs folks that have C++ and Fortran with MPI, and Python is involved in this in a major way, actually. We're looking to drive the system with programming models, so abstractions on how you've heard of ASTs, graph, abstractions on how the system operates, where we're looking to merge MPI plus other technologies. So they call it MPI plus X. And Python also does the statistical driving, the UQ uncertainty quantification and statistics to drive the system. So that sounds like a lot. And some of the things that we are dealing with are trying to figure out questions like, what are the system communication bottlenecks? What are the optimal communication strategies for designing these systems, hardwares, et cetera? What kind of dynamic management and resource distribution is optimal? What's optimal balance of heterogeneity in the system, things like that. And we have to be able to set this up in a way that we can actually answer it both mathematically or programmatically, and then try to build it into the system. Or at least the vendors will build this into the system. I won't be doing that. So we use these kind of abstractions on graph management, nodes, pipes, batch, fork, join, map, abstract logging and caching, communication patterns, memory hierarchies, resilience strategies, system efficiency, etc. And basically, for a lot of these material science codes, what we do is we make proxy models of the, how the material science codes would interact with the system, as well as proxy models of system behavior, because we don't have an exascale system right now. One of the models that is being developed at Lawrence Livermore is called Gremlin, and it basically models failure in the system. So we run it, and it creates bugs and failures and et cetera, and we try to react to it. So as statistical calculations, we basically envision we'll have a couple different kind of calculations, things to try to measure system behavior, design using parameter sensitivity, and then a whole bunch of little things which are basically like agile estimators of system futures. So this is basically like trying to figure out, okay, how is the system going to behave given the current conditions? Let's make a quick estimate and shunt resources there, so dynamic workload balancing, et cetera. So that sounds like a lot of work, and it is, but fortunately, like I said, I have been working on this exact problem for many years, not at the exascale, of course, but the underlying technology was started 2004 under the DOE ASK project and the NSF DANCE project. Both of them were large by academic standards, basically to produce parallel computing frameworks. And under both of those projects, we built Pyena, which is a parallel map for MPI and cluster schedulers. And we built Pathos, which does SSH tunneling, copying, and execution, so we can do parallel and distributed on large machines. So Pathos is still alive and well today and has grown up quite a bit. And at the ends of both of those projects, we started into predictive science analytics, where we built Mystic, which is a flexible class-based optimization framework, where we wanted to be able to play with the optimization algorithm as much as possible to squeeze out behavior, better behavior from it. And we basically added this special way we deal with constraints. We realized that for large systems, penalty functions are limiting and inaccurate. So one of my ideas was, well, we need to apply constraints as functions. If we can apply constraints actually as functional constraints, Python functions are the best constraints, then we can apply them exactly. We can apply them arbitrary boundaries, et cetera. And that actually came, both of these things with the optimizers ended up being something that was a major change for how optimizers were done at the time. I mean, I basically ripped out a lot of the SciPy optimizers to start with, and then started to augment out of them. And problem is, when you put it all together, it didn't work at all. And the reason it didn't work was Python sucks for HPC. There was no serialization. The serialization problems were actually what was killing us. Python does a lot of things right? There's dynamic lazy evaluation, weakly typed, a great mix of functional and OOP. So there's a lot of good reasons why people turn to Python for HPC. It's the same reason that XMetX, this project, came to me for this, is because they were all C programmers and they are interested in some dynamic programming in Python. They heard it was good. They wanted to add me to the project. So in reality, and this is especially in the mid-2000s, serialization in Python, and it still is basically incomplete and it's broken. It's got partial language coverage. There's a big deal about security concerns, right? Don't ever use pickle because your data is insecure. I don't care. I'm not going to be leaving it somewhere for a long time. I'm just going to be passing it around between processors, right? So don't screw me on not using pickle. And basically there's other limitations from the Python stack and the GIL. Basically, the GIL, if you look at a frame object, a frame object relies on looking up the GIL, which is just a number. It's just a float or an integer that's in C that you can't change. That's it. That locks the frame object, and then there's a lot of things that are done with the yield statement. Basically, anything that's an iterator or a generator or built off of that is built off of frame. There's a lot of things that are built off of frame objects in the stack, and they're all tied to the GIL, and that causes limitations in your ability to serialize it, because nothing serializes that is tied to frame objects. So it's basically, with those limitations, and any of you who've tried HPC in Python, there's a lot of good packages out there. You know, you get excited about it, say, I'm going to do multiprocessing. And Python has multiprocessing, so you figure it out, you write your thing up as a map function, you build your pool, you put your function in there, and the thing blows up. It doesn't work. And it doesn't work usually because serialization, right? And you have to follow certain special rules to make it work, and you shouldn't have to. You should be able to do HPC programming like you're just doing regular programming in Python. So it's really stunted the growth of Python as a HPC language, these things right here. There are workarounds. I think there are good workarounds. Copy-reg and now reduce basically allows you to extend the language serialization in Python. And you can do that for almost everything if you have an infinite amount of time. I've been very smart about it and have had several years, so I've done a lot of that. Security concerns, really, not my problem. I did notice that in the code at one time, it used to say, in pickle, you know, throw an exception because of security issues, right? Like, what the hell is pickle throwing exceptions for certain types because they're insecure on the as data stores? That again is not pickle's responsibility. You should use something like RSA authentication if you're worried about storage, right? I mean. So especially for HPC, if you talk to the people who say don't use pickle, when you say, well, I want to use it for parallel computing, then you actually will hear a change of tone. They say, yeah, okay. Yes, you could use it for that. So don't let that. But anyway, the limitations in the stack, really what you have to do is you have to go to C. And so there are ways around it. There's using C. C types. I've started to do some work on this part of the problem using C types to get iterators in a pure Python implementation with C types. And the other route is basically to extract source out of live objects. And then get the code going from that and pack it back into an object. So with dill, basically, dill's features are we can serialize most of Python, pickle code from the interpreter as well as in a file, save an interpreter session for shipping a restart, basically save any edit you make to a Python object's dict and recover from it after serialization, save classes by reference or by definition. Thus, pickles are still valid when the class definition changes. We've got some good diagnostic tools, and we've already started to do things like source code inspection and extraction. So there's some other things that are planned, basically working on the stack. stuff still doesn't work. Basically, at that time, stuff still didn't work. I did a nice trick of when you do import dill, it basically bootstrapped all dill's objects that it knows into the dispatch table, and then basically you get everything without having to register anything. Very nice. So it still, I thought, hey, that'll solve all of my problems, right? Then I don't have to hack all these other packages. I can just import dill and it should work, although that doesn't tend to work all the time because people use cpickle, or like in multiprocessing, there's a bunch of their own conflicting workarounds that end up causing the thing to fail. So in 2009, what I did was forked multiprocessing MPI for Pi, parallel Python, and some other stuff, which these aren't supported right now anymore. But and then stuff started to kind of work. I basically removed all of the workarounds and set up a common API for the blocking map. And I was able to, in kind of a very research grade mode, have multi-parallel Python with MPI distributed and multiprocessing, and do map jobs on the national labs with clusters, basically, and run some large-scale computing. So I extended this to these packages, the stuff that kind of works now, where you get star args and maps and pipes, a unified API for pool, asynchronous iterative blocking maps and pipes, and apply, basically. Run from the interpreter or from a file, so you can run and code just like you're coding normal Python. You don't have to know any threads, sockets, cluster, schedulers, MPI. You basically just build your map and your pipe. And we're looking to extend still, spin back up, go from PyCUDA to OpenCL, 0MQ, some other things like that. You better use shared memory. And do mixed type pools, so you can do dynamic workload balancing. So basically the abstractions on the model look something like that. You just have a bunch of different pools and map functions, and they work just like multiprocessing's interface does. But you can code them from the interpreter or anywhere, and they can interact with each other. And primarily what you have to do is you have to be able to have everything be serializable, especially when you, I'll skip this one, especially when you start to use it for other things. So one of the other things I started to use it for was taking functions and shipping them and serializing them and storing them in temporary backends, so caches. We have a new package called Klepto, which is part of the suite, and it's an API for caching and archiving, and it's basically very flexible for the different backends that you like, and different ways of storing it if you're concerned about using pickle or something else. And this allows us basically to have a distributed parallel hash that can take these Python objects and share them between your different processes. We plan to add HDF, Redis, and a few other things. So the immediate impact is basically we were all of a sudden able to do science, and we're in this new project, PSAP project, which was the job of producing a parallel predictive science framework. And what we went about doing is creating something that does leverage dill and pathos for global optimization. Now we were able to serialize those class-based optimizers. And what we ended up doing was saying, well, let's take this all the way to rebuilding statistics a little bit better, do things now that we have the parallel computing power that people haven't ever done before. So we started doing statistics over all possible scenarios, things like all priors, all posteriors, every potential scenario you can handle, and then write the mathematics to set that up, basically. And what we got were, I'll just flash through some of these quickly. We had built new massively parallel optimizers, things that can run 10,000 way parallel jobs that spawn a bunch of optimizers and have them all very fast steepest descent optimizers run, all talk to each other, and try to figure out what a map looks like. So it's a fast global optimizer. And there's optimization over these probability distributions where we work on a basis set of probability distributions and do the optimization basically in a probability cloud. Our constraints are operators, so it's a little different. If you want to see what the impact was on statistics, we actually learned some new things. I have a poster that you can come talk to me about this. It's actually a very big impact on statistics. I'll make the slides available so you can read it or come talk to me in the poster. We did some science, basically big, large problems, large parameter sensitivity calculations over some of the largest machines in the world on these very big materials simulations, all Python driven. So where are we? I don't know, finish. Is basically this takes a lot of time. It's a problem with a huge scope. We're looking basically we realize that we're not going to be able to solve this problem by ourselves, so we've tried to open everything up to the community. It's on GitHub. I moved everything onto GitHub. I moved the trunks onto GitHub last year at SciPy. I've put out some new releases. Some of the things, the releases are very stale. I've put out some new releases. We formed this nonprofit to help try to support HPC and statistical science. And basically, what can you do? Contribute to Pathos. We have a few contributors. Contribute to any of these great projects with overlapping scope. And really come talk to me if you're interested in looking for funding or jointly seeking funding with the foundation. So thank you. And here's again a short summary, why it's broken, how to fix it, contact me. So thank you.